Video 5, this one's going to be rather short because it's just the language and speech part. Okay, you've got here evidence of what we have got from autopsies. If you've got a patient who had a stroke and after the stroke developed very specific speech-related conditions. So, I mean, I've mentioned the word salad earlier on. You could have difficulties forming the word, you could have difficulties expressing it, interpreting it. Some patients are able to write perfectly, but just the words don't come out. So from the symptoms and the very specific displays of behavior that these patients have, you can kind of keep a record of that, and then once they have passed away, or with obviously imaging techniques, you can see which areas of the brains were actually affected by their strokes and died off, and therefore such and such a process no longer have happened. We've got a lot of evidence of that left hemisphere being responsible, that lateralization, that only one hemisphere is responsible for speech and language. There are 3 areas, plus obviously the accessory area, the fasciculus, I'll come to that in a second. 3 areas of the brain. You've got information coming in. That's mostly auditory, but visual as well. We do look at a person's lips while they're speaking, and it does give us information to process. You then have the area that is making sense of that information coming in, whatever visual and whatever auditory noise is coming in, to interpret that in sort of structure that we then recognize as phonemes and words, and making sense of it that way around. And the last bit, we'll need to get the information out somehow, and then to the motor cortex to then tell the muscles of the mouth, the lips and vocal cords to produce the speech again. So information in, interpreting it, and some sort of information out. Which our areas are there? You've got here the Wernicke's area as the information in, where you're getting from the, sorry, no, that's the processing, sorry. You're getting information in from the temporal lobe and the auditory, you're getting from the visual information through the occipital lobe, you're getting information in. You need to have an interpretation area, and you need to have an area, the Broca's speech area, which gets the information produced outwards. Let's do that nice and slowly. So the actual just information in, not yet any meaning making or interpreting, that's the visual and the auditory cortex, which is in the occipital lobe and in the temporal lobe for the auditory. The Wernicke's area is for making meaning of those words coming in, but actually then making meaning of words you want to produce. The typical Wernicke's area, if damaged, the typical symptoms you would find if somebody is speaking, a banana is happy in the sky and the credit card ran to the flowers and pencils are sad. Some sort of sentence that makes no meaning because the words are grammatically linked correctly, but the words themselves make no sentence, no sense in that context. You will need to get one of the accessory areas that I've mentioned earlier, the arcuate fisculus. That one is where you've got a bundle of nerve fibers that are actually in interplay area between the Wernicke's area and the Broca's area. Okay, so now we need to get an area of the brain that actually then tells the motor neurons which muscles to contract in the vocal cord area, in the mouth and tongue area. So if now the Broca's area, the information out area, is damaged, it's also called Broca's aphasia. Speech can be slurred, slow, incomplete, ungrammatical, but actually the meaning of the words is there. I'm just going to go back in that PowerPoint that you've got those areas again. So we've got information from the occipital lobe, the visual information going into the Wernicke's area. From the temporal lobe, you've got the auditory cortex and the auditory information coming in, meaning making of the actual words, then handed over through the fasciculus over to the Broca's area for speech production. That will then speak to the motor cortex in the frontal lobe to then communicate that with the peripheral nervous system as to what needs to be produced in terms of speech. Now, how else do we know that that information is one-sided, right hemisphere, left hemisphere, mostly on the left? Again, you've got either electrical or chemical ways of either stimulating or numbing the brain and therefore getting information as to when can patients still reply and when can patients no longer reply. If you've got an electrical overstimulation of an area of the brain, then that's disrupted and it can no longer respond or coordinate. So if you're stimulating the right hemisphere, patients can still reply if you speak to them. If you're stimulating the left hemisphere, that will not happen. Or you can chemically numb and anesthetize one hemisphere at the time only. The chemical that is used, sodium amytril, I've not heard of that before in a different context, but if you're an anaesthetist, you will know of your chemicals there. Right, that was short. And the next one is going to actually how we are studying the brain. What techniques do we have? And